Mathematics was born as a way to help us quantify what we do, from measuring the prices of goods to even predict the motion of stars and our future. But apparently not to design. You see, when I was in my first class of my bachelor's, they told us that architecture was the middle point between science and art. Yet, the more I continue my classes, the more I realize that beyond basic geometry, there really wasn't any math involved. A few centuries ago, architects were engineers and also mathematicians as well. So, where did this skill go? Well, it didn't go anywhere. The nature of a profession changed with time, that much we all can agree, which means it can change again. Algebraic geometry is said to have its roots in ancient Greece. However, the main milestone, or at least documented one, is when René Descartes introduced coordinates into geometry. This allowed people to go back and forth between an algebraic treatment of an equation of a geometric object to a more direct geometric treatment of the volume itself. Today, algebraic geometry is helping humanity in areas like number theory and even string theory. The objects studied here are called algebraic variety, which are geometric objects that can be defined by polynomials. A simple example will be a sphere in a three-dimensional space when x, y, and z satisfy x squared plus y squared plus z squared minus 1 equals 0 or equals 1. If the same set satisfy x plus y plus z equals 0, then we get the circle in red. One incredible potential something like this makes you think is that technically you can express a 3D form or the rough volumetric form of a building in an equation, some more complex than the other with the use of integrals and other tools. As a matter of fact, software like Rhino and Grasshoppers have plugins that let you create 3D shapes from equations. In the case of Grasshopper, this plugin is just called the Math plugin. In 2013, the University of Lisboa, in collaboration with the Museo Nacional de Historia Natural y Ciencia, did an exhibition on 3D models made from different equations. If you want a more visual representation, you can use Desmos for free and see for yourself how points are located in a graph that represent the equations in hand. The mathematical approach to design wasn't uncommon centuries ago. Renaissance architects believed that the universe was perfect and that the laws of nature and creations were built upon mathematics. This gave architects a fame similar to philosophers, with many believing that architecture was the way to unite the cosmos and humanity. During this period, Filippo Brunelleschi designed the Florence Cathedral Dome, and he used mathematics in numerous ways. He relied on geometric principles to decide the shape and proportions of the dome. The arcs and bolts were calculated so it can hold the building structural load. But my favorite aspect was the use of trigonometric functions to design the elevation. With it, he calculated the dome's ribs, which made construction possible. Previous domes used wooden framework, but Brunelleschi dispensed this idea. Instead, he relied on his ingenuity and mathematics to create chains inside the dome to deal with the upward and downward thrust. Nowadays, when someone thinks of architecture and math, their mind probably goes to something like building science, sustainability, carbon emissions. Those are great use of math, don't get me wrong, but it's almost as we assume it has no place in the design process, and I believe that's wrong. Austria-born architect Christopher Alexander was a trained mathematician from Cambridge University. Among his work, you can find the influence of math. His PhD addressed the concerns of how to design mass industrialized housing by using game theory, creating a design process that works as a cooperative game between architects and the public. The game's objective was to collect massive amount of data regarding public needs and preference, and architects' own preference and ideals. Alexander suggested imagine the house not in terms of a kitchen, a bedroom, windows, or doors, but instead to think in terms of its own failures, or rather, how its attributes can cause to fail, and associate it with data. Another great work of Alexander is a book he co-authored called A Pattern Language: Towns Building Constructions. It features photos, description, and analysis diagrams of 253 patterns Alexander explored as units for the design of buildings and cities. The sequence and relationship of these patterns are defined by a rigorous mathematical logic, finding over 1800 relationships between them. It is fair to say that this book is both one of the most read architecture books of and is also one of the most criticized ones, due to the radical paradigm shift in the industry.
At least when I studied architecture, math wasn't given much importance, and the way they can influence design was mostly overlooked. It's a skill lost to the profession that used to be a requirement centuries ago. Now, I don't say that every design should be explained through geometry or arithmetics, but I hope this short video can help you realize that math can be a design tool and not just a problem.